This is our lecture number 12. Since you don't see me in class, or at least don't see me that often, I want to make sure that you know who your professor is. This is a photograph of three men of the same age. If you will recognize your professor, you are in good shape. I also want you to realize that by looking at these pictures, one can say what are the political aspirations and political position of a person and how it affects the way the person looks. Now I feel like continuing our lecture. What I will do now is to close this stuff that has nothing to do with adaptive control and get to my lecture, the text that you can also see on the internet. I want to show you how simply one can look at the least square method procedure. I want you to see the array X and array Y that contain measurement data. And this measurement data represent values of the input variables at time 1, values of the input variables at time 2, and so on. And values of the output variable at time 1, time 2, time 3, and so on. Now please take a look at the definition of the model that we want to build using this statistical or measurement data. The output of the model is calculated as a sum of coefficients times appropriate values of the input variables. It is a linear model. And you can write the same expression using vector expression. And this is the matrix vector expression. Here, the model coefficients are represented by vector A. They are A1, A2, A3, AM, where M is the total number of the inputs. Now I can use this measurement data and I can use coefficients. At this point I'm assuming that coefficients are unknown to us to build the whole column of the model value of the output variable. Look, it has model value for time 1, model value for time 2, and so on. To get this result, I have to take this array of input measurements and post-multiply it by the array of coefficients, or vector of coefficients. Or I can write it down in the compressed form. The column of model outputs is equal to the column of measured inputs times vector of coefficients. Of course, from this expression we want to find the unknown coefficients A. What do we want to accomplish? We actually want this product X times A. The array of input variables multiplied by the column of coefficients, we want it to be equal to the column of measured variables. They may or may not be equal to, but this is what our intention is. Now I have this expression written, and nobody stops me from multiplying left-hand side of the equation and right-hand side of the equation by the transposed array of input measurements. Now, let's together assume that this matrix transposed array times the original array of input variables, this is a square matrix, and let's assume that it is non-singular. If it is non-singular, I know it is a square matrix, so we should be able to invert it. And I will multiply the left-hand side and the right-hand side of this expression by the inverted by the product of inverted array times the original array in the power of -1. This is what I will get. However, in the left-hand side, this expression, inverted matrix times the original matrix, it's equal to unity. So in the left-hand side, I will just have the vector of unknown coefficients. In the right-hand side, I will have this expression. And therefore, this gives you a very clear reason for using this formula of the least square method procedure. Now we will get into mathematical description of dynamic systems. And there are two issues there, and we will cover issue number 1 first. Well, you have to realize that if we run a self-tuning control system, the implementation requires a lot of computer programming, computer operation. And since we use computers to implement control laws and to implement additional auxiliary functions of a self-tuning control, we have to operate in the discrete time domain. Therefore, first I will talk about dynamic systems and mathematical description of dynamic systems, and then we will be very specific about building mathematical models for discrete time dynamic systems. First of all, you have to keep in mind that when it comes to discrete time mathematical modeling, the best what we can do is to use z-domain transfer functions. And let's see how the z-domain transfer functions could be obtained. Don't forget that we're getting into self-tuning control only because we do not have very good quality of mathematical description of the controlled plant. So I guess first you have to realize that we're working, generally speaking, in time domain. And what you can see right here is a static, continuous time model that relates immediate values of the output of a dynamic system to the immediate values of the input signal. Now, if we would look into a more realistic situation, we have to deal with dynamic systems. And for a dynamic system, mathematical description is basically a differential equation. And differential equation could be always reconstructed in order to define the highest order derivative of the output as a function of some unknown parameters, and also derivatives of the input of lower order and the output derivatives and output derivatives of the lower order, and finally the output itself. So this effectively is a dynamic model of the control plant. But in many cases, operator phi is a linear operator, and in this case, there is not a big deal of switching a linear differential equation into a continuous time domain or S-domain transfer function. So this is the S-domain transfer function, which presents an ideal way to describe continuous time dynamic systems. However, if we would switch to discrete time, then continuous time will be represented as integer k, discrete time index, times the time step. Instead of output of the system y, we will have output defined as a function of k, where k is a discrete time index, and the input will be defined as u of k, where k is the discrete time index. And of course it is possible only because time step that we use is constant. If this is the case, then the model could be defined as a backward difference equation or recursive formula, and this backward difference equation relates discrete time values of the output at time k as a function of some unknown parameters, of course, are involved, and we have output or at moment k minus 1, output at moment k minus 2, and so on. Finally, the input at time k, input value at time k minus 1, and so on. And of course, k is the discrete time index that starts from 1 and it goes till infinity. However, this was a backward difference equation. Alternatively, we can rewrite this equation in the form of a forward difference equation. So, in a forward difference equation, we have output at time k plus n that depends on some unknown parameters, output at time k, output at time k plus 1, and so on, and finally the output value at time k plus n minus 1. And then value of the input at time k, value at the input at time k plus 1, and so on. So this is the same difference equations. This is the backward difference equation, and this is the forward difference equation. They may describe exactly the same system. However, these linear difference equations, backward or forward difference equations, could be replaced by z-domain transfer functions. So, I am assuming that you are familiar with the z-transform, and yeah, this is equation intended for a backward difference. This is equation or transfer function intended for the forward difference. One way or another, if we will get with you into discrete time self-tuning control, you would have to work with z-domain transfer functions. Where the z-domain transfer functions coming from? Well, if you have a s-domain transfer function, it basically gives you a very good answer. We have to take this s-domain transfer function and convert it into the z-domain transfer function by specifying the time step and also using the zero order hold option. There are many options for this conversion, but the zero order hold option seems to be very consistent with many problems in modern engineering. Now, we can obtain the z-domain transfer function directly from the difference equation. How we do it? We do it using the properties of the z-transform. This property is known as the advanced theorem. This property is known as the delay theorem. So by this theorem, using these theorems, we can take the difference equation and obtain the z-domain transfer function easily. It's exactly like from a differential equation we can get the s-domain transfer function. Now, in many practical situations, the expression for linear dynamic model is already given in the z-domain transfer function form. But we do not know the coefficients of the polynomial numerator and polynomial denominator of the z-domain transfer functions. These coefficients, ai and bi, are unknown or poorly known. And then we have to engage in the problem of estimating these coefficients based on the observation data. You know, earlier, when we've been discussing the least square method procedure, I showed you schematics featuring a control plant, static control plant with many inputs and one output. In this case, we're looking at the dynamic model or model of a dynamic system. And this model since we consider discrete time domain situation, could be considered as the value of the output at time k plus n, where n is the order of polynomial denominator, excuse me, and it depends on value of the output at time k plus n minus 1, k plus n minus 2, and finally yk, and the values, discrete time values of the input, u of k plus m, u of k plus m minus 1, and so on, up to uk. Now, it looks like we are prepared to deploy the least square method approach. This picture basically shows how a single input, single output dynamic process could be treated as a multiple input, single output process. In other words, how we can obtain for a single input, single output dynamic system a difference equation. In this case, it is a forward difference equation. To deploy the least square method procedure, we have to introduce some intermediate variables v and intermediate variables x. And this is the definition of these variables. Variable v supposed to be the output variable, and for our model it is equal to y of k plus n. Variable x1 is actually the same value of the output variable, but taken a little bit early, one time step earlier. This is the same value of the output variable, but taken 2 time steps early, and so on. And finally, some of the input variables, variables, will be used for value of the input signal taken at k plus m time, a value of the input signal taken at k plus m minus 1 time, and so on. So these are the auxiliary variables that we will use to deploy the least square method procedure. How about the vector of model parameters? This is the vector of model parameters, and you have to be able to map it onto the coefficients or relate these coefficients, relate components of this vector of model parameters to particular coefficients of the polynomial denominator and polynomial numerator of the transfer function, or polynomial, or part of the forward difference equation coefficients, and another part of the forward difference equation coefficients. And then, after this designation is done, and after we recognize that these are our unknown coefficients, we can use Rls M procedure in order to estimate a known parameter C based on the observation data. How we build this observation data? We do it exactly the way we do it in the least square method procedure. Whatever we call the first measurement of all inputs is right here. x1, x2, xn plus m, xn m plus 1. They are values of the output variable at particular time, value of the output variable at the next time moment, and eventually values of the input variables taken at different moments of time. But according to our designation, they all are treated as measurements of the multiple inputs taken at time 1. The next row should be the measurements of all these inputs taken at the next moment of time. And again, I want you to realize that among these inputs, we have values of the system output and values of the system input. And so on. And we have to accumulate an array of total of capital N measurements. And you have to know that the capital N is supposed to be significantly greater than the number of unknown coefficients. N, in other words, should be much greater than 1, much greater than 1. Now, what you have here are the values of the output variable V. You remember that designation, this actually is the output of the plan taken at some k plus n moment of time. And this is the next measurement, and next measurement, and so on. I would tell you that the most difficult part is to come up with these designations for k equal to 1, for k equal to 1. And then everything will be easy. And we will talk more about this. Now, don't forget about the definition of variable k. K is a variable k for variable v, the discrete time index for variable v. It starts from k. K is supposed to start from 1. But don't forget that this v of k, or v of 1, is equal to output y at time 1 plus n. So we're looking into some future value. And then we relate future value of the output to the value of the output times 1 time step earlier, taken 1 time step earlier, value of the output taken 2 time steps earlier, and so on. You know, it's not that convenient and not that convincing to discuss these designations in general. What I want to do is to take a very particular model where y of k plus 3 should be equal to minus a2 times y of k plus 2 minus a1 times y of k plus 1 minus a0 y plus k plus b2 times u k plus 2 b1 times u k plus 1 and bu and b0, excuse me, times u of k. It is a forward difference expression. Forward difference expression. Now, how to work with this expression? The best that we can do is first of all, I want to clarify this forward difference expression. To get this forward difference expression, I can take the transform of this expression, take advantage of the advanced theorem, and I will get this transfer function. So I guess this transfer function and this forward difference equation represent the same system, the same order. However, this is done in the z-domain, and this is done in the discrete time domain, and we should have no difficulty switching from this form to this form, and from this form to this form. However, we need this form, because this form will be necessary for the utilization of the least square method procedure. Now, what are the auxiliary variables? What the auxiliary variables are for this in this problem? These are the auxiliary variables. I will introduce variable vk, k is a discrete time index, and I will say it's equal to yk plus 3. I will introduce a variable x1. I will treat it as the input variable, but it will be equal to minus yk plus 2, and so on. Then I will have variable x3 and x4, x5, and x6. How the vector of coefficients of the model would look like? Well, it will have a2, a1, a0, b2, b1, and b0. So this part is easy. How to define the model? We will define the model as the vector of unknown parameters transposed times the vector of inputs. The vector of inputs is spelled out right here. It's very consistent with this designation. I will give you a very good example of the definition of data array of input measurements xn and data array of output measurements vn. I'm building this data array xn. For the first row, I have, this is x1 of k. This is what I used to call x2 of k. This is what I used to call x3 of k, x4 of k, x5 of k, x6 of k. But then you have just to increase these numbers. So the next will be this row corresponds to vector x at time equal to k. This is vector x for time equal to I have to back up. This row represents the vector of inputs, vector x, for k equal to 1. This row represents the vector x, k, for k equal to 2. Next is next row should be vector x for k equal to 3, and so on. And finally, this is the vector x for k equal to capital N. Now it's not a big deal to define the column v representing numerical values of the output variable. By the way, if you care, please realize that if this is vector of input measurements x, this row for time equal to 1, this row is vector x transposed. Vector x transposed for time equal to 2. Vector x transposed for time equal to k. So this is exactly what this expression tells you. What do we do in order to apply the least square method procedure? Well, we have to record values of the input variable and the output variable of this single input, single output controlled process. And you have to do it for k equal to n plus 1, n plus 2, n plus 3, and so on. Then we have to build the array of unknown coefficients, and this array will be defined by this expression. And this expression is the formula of the least square method. And after this expression is obtained by the least square method procedure, what we have to do is to properly disperse, utilize elements of the vector c obtained by through this equation. And we will get components of the z-domain transfer function that relates y to u. You know, I want to remind you that the zero-order hold notation probably, or a zero-order hold conversion, probably is the most practical in modern engineering, and therefore I want you to keep in mind that if you will go through this route, and if you would eventually get this transfer function would be consistent with the transfer function that you would get otherwise from the S-domain transfer function for zero-order hold option. And we'll talk a little bit more about this, and I want to show you the numerical example. At this point, according to my numerical example, I'm assuming that I know the order of the polynomial numerator and polynomial denominator of the transfer function. These orders are known, but the coefficients are unknown. Now, we will be getting these coefficients by using the least square method procedure. We will be getting these coefficients by processing some measurement data. Obviously, we don't have a real control plant. We cannot perform measurements on the plant, but we can choose so-called true control plant defined by true S-domain transfer function, and we will treat it as the real plant from which measurement data will be taken. What shall we do if this transfer function is chosen and will be used as the true control plant? This schematics shows you that I'm using a simulator. In the simulator, I have this control plant. The output of the control is Y. This is the input signal that drives this control plant, and I will call the signal U. This is facility in my simulator that enables me to store the input and output data. And the rest is very easy. I have to create the input, and I'm creating input as a combination of several sinusoids and a random signal. You don't see the part of the simulator that creates the signal. And then I apply it to the system. And then the signal I apply directly to the plotter. And I'm getting this graph that shows us red is the signal that we apply to the input of the plant. Blue is the response of this plant. And this data is stored somewhere in the numerical form. And what we have to do is only to extract array capital X and extract array capital Y, and then apply the least square method formula. Now, I want to show you additional insight into the solution of this problem. My measurements cover only 50 points. The time step is 0.05 of a second. K is the discrete time index, and I show you in this table, you can see the set of input and output measurements. And of course, they are synchronized input and output measurements. It's a single input, single output system, so don't be surprised. You see only two columns plus the time column. The next that you can see that I am putting together the array of input and output observations. This is yk plus 3, which is supposed to be eventually the output y. Look, I'm taking it at the value 1 plus 3. K is equal to 1, and 1 plus 3 is 4. Right here I'm taking the value of the variable. Now, this is yk plus 2, and I'm taking it at the appropriate value. So in terms of timing, I can assume that this column is shifted up by one position. This is yk plus 1. It is again shifted up by one position with respect to column 2. And finally, this is output y of k, and there is no time shift. You can see that it's taken at time equal to 1. The next, you can see the input signal. It's supposed to be taken at time equal to t. The next value should be taken at time at t plus 1 and t plus 2 and so on. So this is the table that I get. Now, if you would follow this part, this part is consistent with the appropriate section of column for y, for the output. Exactly the same thing. This part, this column, is consistent with the input-output data for the output, and so on. The next that I have to do, I have to lift this column up by 3 positions. This should be lifted up by 2 positions, by 1 position. This should be left alone, and by doing so, I will get an array of output variable y. And then I would perform shifting on these 3 columns, and eventually I will come up with the array representing all input measurements for our system. You see this array right here. And look, this part of the array I call xn. And the left part of the array I call yn. I'm ready to do the least square method problem. I have the data that I need. Now, when you will be working on your homework assignment, it's advisable to look through these tables very carefully, compare these tables with the data you have, and you will be able to build tables. Now, I have to show you the results of this work, of course. Listen, I have to go back. You saw table 1 containing the input-output data. You saw table 2 that shows array xn, how array xn and array yn are built. Finally, you show arrays xn and yn as they should be inserted in the least square method procedure. Now, if you would use least square method procedure, as I did, you will get vector c. And after you get vector c, you should be able to map it onto the discrete time domain transfer function g of z. Finally, the transfer function g of z right here, and you can see it. It was obtained by taking the original S domain transfer function and converting it into the Z domain using the zero order fold option. Results are not bad at all. Not bad results. Which one you will trust? Obviously, this one is a more accurate one, but this one is a practical and a good result to use. We will talk now about mathematical description of dynamic systems 2. In many applications, a single input, single output control plant is represented in a state variable notation, and this state variable form has the state equation and the output equation. Now, in the left-hand side, we have the state vector taken at time equal k plus 1. In the right-hand side, you can see the fundamental matrix of the system times the state vector taken at time k plus matrix B times scalar, which represents the control effort. And the output is also scalar. It's a single input, single output system that is equal to some matrix C times the state vector taken at time k. And I spelled out here the state vector definition, the fundamental matrix, matrix B, and matrix C. I am assuming that our system is a mth order system. Now, parameters of the matrix A, parameters of the matrix B, and parameters of matrix C may not be known. And in order to utilize the state variable description for our control applications, we probably would need to estimate unknown parameters. How to estimate them? Of course, from the measurement data, like we did it in the least square method situation. And it will be a least square method estimation, of course. So, first, in order to estimate these coefficients of matrix A, matrix B, we have to consider individual state equations. For example, what you can see here is the state equation for line number I. And for this line number I, we have coefficient I1 times x1 plus coefficient I2, A2, I2 times x2 plus coefficient ij times variable j, and so on. In the end, of course, you have element I of matrix B times the control effort U. All these variables are taken at time k. Variable V is supposed to be the output, but for this output, we will use V of k equal to xi times k plus 1. So what we are effectively getting the row number I of this matrix equation. When it comes to estimation of parameters C, you can see that output y for time k is defined as C1 times x1 plus C2 times x2, and so on. And we have total of m terms and m unknown coefficients in this equation. How to estimate parameters? Of course, based on the known input and output data. Measurements of x1, x2, x3, x4, xm, and measurements of u, and measurements of y that could be recorded during the process operation. So what should you realize from what I just said? You have to realize that when it comes to estimation of the parameters of the fundamental matrix and parameters of matrix B and matrix C for state variable description of the control plane, we follow the same least square method approach, but we have to apply it 1, 2, 3 m times plus one more time to evaluate coefficients of matrix C. I do not anticipate the use of this parameter estimation in this particular course, and therefore I will proceed with the material that must follow. I want to talk now about the recursive least square method technology. You know, the recursive least square method was invented one of the brightest people known to mankind, Rudolf Kalman. Kalman died 2 years ago, Kalman was indeed a great mathematician who made a tremendous contribution to control engineering. As a matter of fact, he is the one who invented the state variable approach, matrix vector description, various techniques like pole placement, eigenvalue assignment, and so on and so forth that are used in the modern control. You know, LSM procedure is quite formidable procedure primarily because it contains matrix operation. Matrix operation is one of the most difficult, time-consuming procedures used in numerical analysis. But then you have to realize that this is not the only problem with the least square method procedure. The situation is this. Let's say we estimate parameters of a control plane. We accumulated the total of n, capital N observations, and we get the results. But you and I know that the more observations are taken, the better result is expected to be. So then we're getting a new measurement. What to do now when the new measurement came? It looks like we have to take this huge data array xn and add one row in the bottom of it. We have to take this huge data array y and add one element at the bottom of it. And then we have to go through the entire least square method equation, which includes matrix inversion and so on and so forth. So our computational difficulties with the least square method has two sources. One source is the complexity of the LSM procedure that has to be, or it looks like it has to be rerun each time we're getting additional data. And difficulty number two, we have to be concerned about an ever-growing data array that contains this input-output measurements. How to address this situation? To address this situation, first we want to do, and actually this is the exactly description of what I just said, illustration to what I said. Look, we got additional measurement, array x, the additional array x has to be augmented by additional measurement. Array y has to be augmented by additional measurement, and then we have to solve for unknown coefficients again. And this time we will get unknown coefficients that utilize n plus 1 data points. And obviously there will be time when additional data point will come, and additional data point will come. And it looks like we will be having exactly the difficulty that I was referring to. How to get out of this situation? First of all, I want to introduce to you recursive computations that are quite often used in statistical analysis. Listen, let's say you want to compute the mean value of some variable z. You're getting z1, z2, z3. They are individual measurements, so individual random variables. And for these random variables, you have to get the mean value. And you know how to get this mean value. You have Zn with bar on the top, which is the mean value that is based upon total of n measurements. It is equal to 1 over n, sum of all these elements from 1 to n. This is how we compute mean value. What happens if a new measurement arrives? If new measurement arrives, we would be having this calculation. It looks like we have to start all over again. Now we will have the mean value calculated for n plus 1 variables. It will be sum of all these variables from variable 1 till variable n plus 1 divided by n plus 1. Nothing new about this. This is what we do. And again, although the summation and division is not very difficult to perform, we may be concerned about the ever-growing amount of data points that we have to accommodate. I will make some simple algebraic transformations, and at your leisure time, review these transformations, but then I want to tell you that these transformations lead to a well-known recursive formula for mean value. This means that the new mean value that is based on n+1 measurements is equal to the earlier obtained or old mean value that was based on only n measurements, plus this correction, and this correction has n+1, new observation, minus the old mean value. And this has to be done again and again for n equal 1, for n equal 2, n equal 3, and so on. And I have to tell you that if the number of variables becomes large, the advantage of this number of observations becomes large. The advantage of this recursive formula should not be underestimated. It's very attractive. And again, our gain is in our ability not to perform computations again and again and again, and not to deal with an ever-growing data array. What do we have to store actually in memory? We have to store old mean value, new observation or new measurement, and the total number of observations. That's it. Very convenient. This principle of recursive computation could be engraved, could be incorporated in the least square method procedure. And this would address the necessity for storing an ever-growing array of measurement data. But least square method procedure also requires to perform matrix inversions again, and again. How to handle this situation? This is the moment when we have to appreciate Kalman's contribution. Kalman came up with a matrix inversion lemma. This lemma of Kalman, and it could be proven only by performing computations. Numerically, it could be proven. Kalman showed how to perform matrix inversion without actually performing matrix inversion, how to perform matrix manipulations, simple matrix manipulations that would account to matrix inversion. And of course, they are not that complex. If you're interested in the derivation of the recursive least square method procedure, I can recommend you to take a look at my book on process control, or just be patient, and a year from now, I will be teaching process control course, and in the process control course, I get into the derivation of the recursive least square method procedure quite in many details. However, the bottom line for our self-tuning control is the algorithm for recursive least square method. This algorithm consists of 3 steps. Step number 1 is to calculate Kalman gain. Everybody calls it Kalman gain to appreciate Kalman's contribution. We call it K. It has index of iteration or index of step of the procedure. It is equal to some matrix P. It's a square matrix. and it's supposed to come from the previous step of the procedure, times the new measurement or vector of new measurements xn, and then this is looks like a matrix operation, but it is not. This is 1 plus transposed vector of input measurements times square matrix P that came from the previous step of the procedure times vector of input measurements. Look, this is 1 times m. This is m times m. This is m times 1. What I have here is a scalar, actually. So this inversion is not a big deal. Inversion of a scalar still is a simple operation. So this is the step number 1, calculation of the Kalman gain. The next what we do is step number 2. At the step number 2, we compute the new parameters. This is the vector of new parameters of the model, or new estimate of the model parameters. It is estimated at the iteration number n. It is equal to the set of parameters obtained at the iteration number n minus 1 plus matrix Kn, the Kalman gain that was earlier obtained, and what you have in this parenthesis is the new measurement of the output minus new measurement of the input vector transposed times all parameters of the system of the model. Yeah, I can tell you this, for example, that what you have in this parentheses is the error between newly acquired output measurement and the calculated value of output that utilizes new input measurements and the old set of parameters. One way or another, this is the vector estimate of the vector of unknown parameters obtained at the iteration number n. But now what we have to do, we have to make a provision for the next step. For the next step, which will be step number n plus 1, for the step we have to compute matrix P, and this is the formula. This formula includes unit matrix, matrix Kn that was earlier obtained, a new vector of measurements transposed, and old matrix P from the previous step, the one that was used earlier. And we have to perform these iterations each time a new measurement arrives. So this big N is equal to 1 and 2 and 3 and so on and so forth. Now you may tell me that when we get into the procedure, when we will start the procedure, N is equal to 1. So we need P matrix with 0. And we also need coefficients A with index 0. And we need matrix P with index 0. How do we handle this? It is commonly recommended that for n equal to 1, matrix P0 should be defined as some positive constant, alpha times unit matrix. And we'll talk a little bit later about the role this constant alpha plays in the least square method procedure. As far as initial values of the parameters, say 0, the better they are, the more accurate they are, the more close they are to the true values, the better will be the convergence of the procedure and the performance of the recursive least square method algorithm. And I have to tell you something. You know, this type of Rls M procedures are used in advanced by advanced industries for advanced technology applications. And for advanced technology applications, most control processes are very well studied, very well investigated. So it's not a big deal to come up with a very accurate initial set of parameters A. However, if you know absolutely nothing about the control plane, for initial values you can use zeros, and this will not be detrimental for the Rls M algorithm. I want you to take a look at the block diagram of the recursive least square method procedure. First is the initialization. You have to make provision for acquiring good initial values for parameters A. They will become A0. You have to define initial matrix P0, which will be constant times unity matrix. The next you will make n equal to 1. Then you have to acquire measurements x and measurements y corresponding to n equal to 1, the first set of input-output measurements. The next you compute Kalman gain. The next you update the parameters. The next you compute matrix P for the next step of the procedure. And then you get into a critical point. Should you stop or should you continue your procedure? If you have to stop, you may print out parameters an or send them to where they are supposed to be used. And if it's not time to stop, and you probably would have special stopping criterion for the procedure. So if there is no need to stop the procedure, you will make n equal to n plus 1. In other words, increment n by 1. Go back to the acquisition of the input-output measurements, define Kalman gain, and proceed within this cycle. I want to talk to you about the properties of the recursive least square method procedure. The issue number 1, if you perform sufficient number of iterations, then conventional recursive least square method is expected to produce the same parameter estimates that the least square method procedure will produce. And I'm using word conventional because a little bit later I will talk to you about recursive least square method procedure modified. Here we have the least square method procedure represented by the formulas that you saw before. So properly operating RLSM will give you the same results as the LSM. The next that you have to know that the results obtained by the RLSM procedure are independent of the initial estimates A0. And as a matter of fact, they are independent of the alpha that we will be talking about a little bit later. So you see, the only what you have to achieve is to be able to run this procedure for sufficiently large number of iterations. And then parameters an will be practically independent of the initial conditions. The next I want to talk to you about the Rls M convergence pattern that depends on matrix P0. Matrix P0, as I said earlier, is defined as a constant alpha times unit matrix, where alpha is positive. And you know what? Effect of this alpha could be compared with the effect of the constant gain in a simple control system. Let's say second order plant with a negative feedback has gain equal to alpha. So what will happen in a system like this? How the step response will look like? If this feedback gain is small, in other words, if alpha is small, the system, the unit step, will still converge to a constant value. However, the convergence process will be very slow, slow exponential process. As you will be increasing value of the gain in the feedback, or value of parameter alpha in the initial matrix P, you will be getting shorter settling time, eventually you will see the overshoot, eventually overshoot will become quite significant. So what do we do in a situation like this? How to choose alpha? There is no rule for choosing alpha. For many years, for alpha, I choose value of 0.05, and then I corrected by running experiments. Alpha could be increased if system converges too slow. Alpha could be decreased if you see this undesirable overshoot. And eventually, in a particular problem, with a particular input-output data, with a particular level of noise and the correlation between input variables, you will come up with an alpha that would satisfy your expectations. Now let's talk about Rls M and measurement noise. If you remember our discussion of the least square method procedure, we divided our noise, measurement noise, in two categories. One category is the input noise, another category is the noise in the output channel. And you know that noise in the output channel, in the output, does not result in the computations. This noise will be rejected, or the effect of the noise will be reduced if you would run procedure for if you would utilize for the procedure more data points, more data measurements. So noise in the output could be addressed properly. Noise in the input will result in the biased results, because regardless of how many data points we use, noise in the input will result in some kind of residual correlation matrix, diagonal correlation matrix, that would cause bias in the parameter estimates. You know, unfortunately, when we do the work with a dynamic system, we know that there is no distinction between input variables and output variable. The output variable is the output variable per se. However, the input variables include the output variable shifted in time, the output variable shifted further in time, and so on. And then the input variable shifted in time. So I guess noise, if it exists in the system, will be always there, and will be very difficult to differentiate, or impossible to differentiate with the input noise and output noise. So if noise will become a problem, you would have to look into the ways to reduce this noise, perhaps by using special filters. Then there is another issue, also quite complex. Rls M and cross-correlation between input variables per se. Input variables. You know that input variables in the case of Rls M is the output variable shifted by a couple of steps, output variable shifted by 3 steps, input variable shifted by 1 step, and so on and so forth. So since we have only 2 variables involved in the input vector, these 2 variables are expected to be correlated. It will be autocorrelation, it will be cross-correlation, they will be correlated. Now, correlation not necessarily will prevent our procedure from being successfully executed. However, if this cross correlation will exceed some limits that nobody can suggest in advance, the procedure will not be converging, and will not converge. You will be seeing ongoing oscillatory random oscillation in the parameter estimates produced by the Rls M, and the parameter values would never settle to a particular value. So there will be no convergence. And actually, in this case, Rls M is even worse than LSM. LSM will just die if the correlation level will exceed some threshold. It will not work. You will get the singularity of the matrix that you're supposed to invert. In the case of Rls M, there will be no message to indicate singularity, but there will be no convergence, period. And I have to tell you that cross-correlation between variables could be eliminated. There are special orthogonalization procedures for doing it. There is principal component analysis that could be employed. And if you would take a look into the text, process control into my text, and of course there are many other good textbooks, you will see the look for orthogonalization in least square method estimation, and you will find some good numerical techniques that you could implement. Finally, in this lecture 12, I want to talk about estimation and tracking. Please take a look at the Rls M procedure. It gives you a formula to compute coefficients, unknown coefficients of the controlled process. Now, you also know that the more observations we use, the more accurate results supposed to be. And if you would take a look at this procedure again, you will see that every single observation will be equally contributing to this parameters A. However, if our set of observations covers a very long period of time, you should realize that any realistic control plan may exhibit parameter drift. Why? Because of catalyst is dying out in the chemical industry, fuel is being consumed in an aircraft, and on and on and on. So there is some degree of parameter drift in any control plant. And therefore, if we would use LSM as it is defined here, it will be very counterproductive to have equal contribution of all measurements into the parameters. These parameters will present very averaged description of the properties of the control plant. In control, we want to have immediate properties, not average properties. So how to handle this situation? We have to find a way how to build coefficient estimates based only on the most recent observations. Not on all observations, but only on most recent observations. I may restate this requirement a little bit. We want to maximize weight of most recent observations and minimize weight of old observations. So this is called least square method procedure with forgetting factor. With forgetting, the old observations are prevented from making contribution or making significant contribution into the parameter estimates. How to handle the situation? To handle the situation, we have to introduce in the Rls M procedure so-called forgetting factor. And procedure with forgetting factor will look like this. We still have to compute Kalman gain. However, it used to be 1. Now it is beta. Beta is a special forgetting factor, we call it. It is greater than 0 and less equal than 1. When we update parameters, beta is not involved, but when we calculate matrix P for the next step, we use 1 over beta instead of 1 in front of the this parentheses. And this beta is supposed to be applied at every step, at every iteration, iteration 1, iteration 2, iteration 3. How this forgetting factor works? This forgetting factor results in the domination of the last M observations in the parameter estimates. The contribution of the last M, capital M observations will be dominant as far as the values of these parameters are concerned. What is M? M is defined as 1 divided by 1 minus beta. And M is called the memory of the procedure. Okay? Now, what will happen if beta is equal to 1? Then memory of the procedure will become infinity. And we're basically going back to the original formula of the recursive least square method procedure. In the original least square method procedure, all parameters, no matter how, all measurements, no matter how many measurements we have, they equally contribute into parameter estimates. We have infinite memory. If we would have B approaching 1, we will be getting procedure with limited memory, but quite sizable memory. If beta is approaching value of 1, it shall not be equal to, will be approaching value of 0, excuse me. If beta approaches value of 0, our calculations, our estimated coefficients will be based on a smaller and smaller and smaller group of the most recent measurements. All right, if we would make beta equal to 0, memory will be equal to 1, and our procedure will become a bogus procedure, because what we do with LSM is statistical estimation, and statistical estimation requires that the number of the observations, volume of statistical data, will be sufficiently greater than the number of parameters we want to estimate. Now, if we run the Rls M version with a finite memory, let's say beta equal to 0.9, for example, this means that our computation of coefficients is based on what? 1 minus 0.9 is 0.1, 1 over 0.1 is 10, is based on the last 10 observations of the process. And we effectively forget the entire prehistory of the properties of the control plant. What we do in this case, we perform tracking of the properties of the control plant. So, if we use forgetting factor, our estimation procedure turns into a tracking procedure when we follow changing parameters of the control plant. And then I have to tell you this: if we will have very small memory of the procedure, we will get the ability to track very fast changing process. But the other side is that we will be losing the ability to reject noise in the procedure. Our approach will be not quite statistical approach. However, if we are interested in addressing or averaging out, I like this word, averaging out noise, then we have to have a greater memory of the procedure. But as memory of the procedure becomes greater, we're losing the ability to track the procedure. So, if you would show the averaged error of our modeling as a function of the memory of the procedure, it would be a curve with minimum. And this minimum will be reached at some optimal value of the memory, because if memory is too small, error of modeling is suffering from the measurement noise. If memory is too large, then the accuracy of modeling is suffering because of our inability to track changing properties of the plan. I guess there is an optimal value for the memory of the procedure that presents a good compromise between these two tendencies. And then, of course, I want to offer you homework number 7, and you have to read through this homework number 7, and this homework number 7 would require you to use some MATLAB programming, and I think that it is doable for people in this class. And then you can take a look at another homework assignment number 8 that also requires you to work with the Rls M procedure, perhaps get some insight in the operation of the Rls M procedure. And then I'm not going to give you homework number 9. I will give you a take-home project that I will accept in lieu of your final exam. So see you soon.